Hi, this is Brian Durand with Machine Vision Store. Let's take a look at the components needed to build a computational imaging system. This is the second video in our series on computational imaging. I suggest looking at our first video, What is Computational Imaging, prior to watching this.
As a quick review, computational imaging involves capturing multiple images of an object. The purpose is to gain additional information about that object. The information is then used to synthesize a composite image. If we have designed our system appropriately for a specific imaging task, this composite image will enable superior inspection results far better than any of the individual input images. The components of a computational imaging system are similar to any vision system, but with some twists. We'll need a camera, lens, and light. We'll usually need a light controller, and we'll need software capable of using the raw input images to build a composite image. To gain this additional information about an object, we can vary light, camera, and lens settings. For example, we might project light from different directions, adjust the camera exposure duration, and/or tweak the lens's focus. The key is to vary the settings in a controlled, repeatable manner. For example, we wouldn't project light from some random directions. We would want to project light from specific directions in a repeatable sequence. For the purpose of this video series, we'll assume that the input images must be captured and processed quickly. If your objects are in motion, the capture speed is critical. We'll need to capture all the input images before the object has traveled outside our field of view. And even if your objects are not in motion, you may have a user doing some manual operation and waiting for the result. As you might imagine, the light, camera, and lens must be tightly integrated to perform a rapid imaging sequence. The devices must support timing intervals set in microseconds, not milliseconds, if the task is going to be completed quickly. This generally precludes the use of Ethernet and PLCs to coordinate device actions. Instead, we're going to use fast hardware signaling between devices having firmware running on bare metal. And we're going to do this using commercially available off-the-shelf hardware, no custom hardware required. A simple example of computational imaging is the building of a high dynamic range image. Cameras can have trouble capturing detail in both the darkest and brightest areas of an object. Either the dark features are completely black or the bright features appear white. But what if we need to inspect both the darkest and brightest areas? The solution is to capture images having different intensities, then combining information from these images together into a composite. There are 4 ways we can get images having different intensities. 1. Vary the light intensity for each image. This is the only method that does not have a side effect. 2. Vary the camera's exposure duration, being careful not to introduce blur from motion. 3. Vary the camera's gain setting, not ideal as higher gain increases image noise. And 4. Vary the lens's aperture, not ideal as it requires a motorized lens, changes the depth of field, and can affect image quality. For this example, our object was stationary. We chose to use a Bosler Ace 2 Pro camera. It has a sequencing function that can automatically change the exposure duration prior to capturing each image. We use Hypal software to easily configure the camera and build the composite image. We could have instead used Zebra Aurora Design Assistant software, but it would have taken us longer to create a flowchart. The resulting HDR image has 16-bit depth, which cannot be displayed on a computer monitor. Hypal uses tonal mapping to convert the result back to an 8-bit depth. The image's darkest and brightest features are now revealed for inspection. Another example of computational imaging is focus stacking. It is common when imaging small objects under magnification to have insufficient depth of field. Simply put, an object cannot be kept in focus. Either its height varies too much from one object to the next, or the object itself has features too near and too far from the lens. The solution is to capture multiple images of an object, each captured at a different focal plane. We use a special lens made by optoengineering to do this. The lens includes a liquid element that can rapidly change the lens focus when a voltage is applied. Unlike using a motor, this device can shift the focus in a few milliseconds and is rated for over 1 billion cycles. We used Hypal software to control the liquid lens and blend together the resulting stack of images. Each pixel in each image is assigned a weight based on how sharp it is focused. The weights from each pixel are then used when building the composite image. The result is a single image having everything in sharp focus.
We've looked at the components necessary to build a computational imaging system, how they require tight real-time integration, and we looked at two examples including high dynamic range imaging and focus stacking. We've not talked at all about lighting. It's a very important topic to computational imaging. It really deserves its own segment. We hope you'll continue watching our next segment.